Hello students, good morning to all of you. Students, in the previous lecture, we will learn about the characteristic of the interference and the superposition principle. Now we will start or we will learn in this lecture about the fringe pattern and fringe width by using the principle or experiment Young double slit experiment. Okay, so topic is interference of light, in which we start Young's double slit experiment. Okay, this is also called YDS. It is a most important part of your unit 6. Okay, and in this, as we learn, just we will recall the condition. Suppose we have a source S and there is a obstacle applied in the path of the source, and that obstacle provides two sources S1 and S2. Okay, as you learn, every wave or wavefront produce the wavelets, and every wavelet behave like a wave. Okay, so if the wave are starting from this source in such a way, then after some time it will reach at S1 and S2, and here the secondary wavelet emits, or suppose we have a screen in front of these two sources, then the wave from S1 are traveling such a way, and wave from S2 also traveling in such a way, and then after some time they will reach towards the screen. Okay, so suppose the screen is placed at a distance d. Okay, at where the waves hits hole on the screen. Okay, so let there be a point at x height above the screen at where we need to calculate the fringe pattern. Okay, let's say this point is P. Initially, the rays are reached on the screen, so in the parallel path, or we say this distance or about this bit, the maximum intensity of light reached there. Okay, so now we will start again. We don't need the initial source, because this we use only to get the two covalent sources S1 and S2. It is clear? Okay. Let the distance between the two sources is small d. Okay. Now, O is the central point of the two sources, and this point is O dash. Okay. So, initially we will say that the distance between O to O dash is d, and the distance of sources S1 and S2 to O dash is equal. Okay, here B is very smaller than capital D, first condition, and let The light traveling from this S1 source reached at P, okay, and light traveling from S2 source reached at P after a time, okay. So there should be a path difference between the two paths S1P and S2P. We need to find the value of that path difference to get the fringe pattern or interference at point P. Okay, so first we will start. Let two coherent sources S1 and S2 at distance small d and a screen let's say xy. A screen xy is placed at capital D distance from S1 and S2. Okay, next. O is center point of source S1 and S2 and distance between, okay, this. So let distance between S1P S12P and S22P is S1P and S2P. Okay. Now one more. The wave from S1 and S2 reached at same time and same phase at O dash. Therefore it is there is no path difference. But the path length S1P and S2P are different. Therefore, the path difference del x is given by S2p minus S1p. This is your equation first. Okay? Here, now we need to calculate the path difference S2p and S1p. So, by completing the two triangles from S1 to A and from S2 to B, okay, because O is central point, therefore this distance is equal as this, so it is d by 2 and this is also d by 2. Clear? Because the sources are separated by a distance d only. Therefore, in triangle S1PA, S1PA, distance from A to P is, distance from P to A is x, that I will write here. P to O dash is x, therefore this distance is x minus d by 2. Clear? And the distance from P to B dash, okay, here P to B is x plus dy. Clear? Therefore, in triangle this, by using Pythagoras theorem, we will calculate S1p square is equal to d square plus x minus d by 2 whole square. Okay, and in triangle S2PA, clear? S2p square is equal to d square plus x plus d by 2, x plus d by 2 whole square. Okay, therefore S2p square minus S1p square is equal to d square plus x plus d by 2 whole square minus d square plus x minus d by 2 whole square. Clear? Now I will expand it or do direct? Direct. Okay. So d square and minus multiply inside the second bracket, so d square is cancelled.
So x minus d by 2 तो पहले आना चाहिए.
We are using x S2p square. Okay. Then when we open this a plus b whole square bracket, this x square cancel by this. Clear? Therefore, we get from here 2 d by 2. Okay? और 1 minute.
So S2P V triangle S2P V.
From here we will get 2 x d by 2, and from here 2 x d by 2. Clear? Okay? Therefore, this is cancelled. So we get from here finally 2x D. Here, if there is any problem, then I am just explaining you how it will be. See here, when you open the square, x square plus this first, b square by 4 minus 2x d by 2, okay, and minus this x square plus b square by 4 and minus 2x d by 2. Clear? A plus b whole square, a minus b whole square. When this minus multiply inside the bracket, x square cancel by x square, d square cancel by d square, and this 2 cancel by the denominator. X d is positive, and when minus multiply inside, this will also become positive, so it will be 2x. Okay? Yes, done? Okay. So, this we have S2P minus S1P and S2P plus S1P is equal to 2xd. Clear? Now, initially I will instruct you that b is very smaller than d. Okay? Second, small d is in millimeter and d is in meters. ये एक प्रोफार्मा होता है to demonstrate the practical. Okay, so now for the experiment or to explain the mathematical geometry about the experiment, these S1 and S2 appear to of far distance, but it is very small distance as in mm. So S1P similar to S2P and these are similar to D. Okay, like this. If these are very near to each other like this, S1 and S2, and the source is here, so the light traveling from here to point this and from here to point this is very near to D only. Suppose we have the distance between the screen and the source is 1 meter and this point P is 0.3 meter, 0.03 meter. So S1P will become 1.03, okay, and S2B will become 1.04. So these two values are near to D only. Okay, so we will use here D. So S2P minus S1P is D plus D is equal to 2x D. Therefore S1P S2P minus S1P is equal to 2xd upon 2d. Clear? So S2P minus S1P is equal to xd upon d. This is your path difference between the two sources when the ray reach to P and superimpose to each other. Okay? So there should be two situations. One is the crest and crest of the two waves reached at P, or crest and top of the two waves reached at P. If the crest and crest reach at P, so the amplitude become double times, 2 times. And when crest and trough reach at the same time, so amplitude will become 0. So when the amplitude become double of each other, so we get the bright fringe or constructive interference, and when the crest and trough reach of the two sources, so we get the dark fringe or destructive interference. Now we will calculate the point of bright fringe at P and point of dark fringe at P. Okay, this is your equation P. We have another method by using the binomial expression, but it is easier for the bio students, so we will do this also. First, for P is a bright point. P is bright point. Or constructive interference. Okay, the path length S2P minus S1P is equal to n lambda, and we have this value is equal to xd upon capital D is equal to n lambda. Therefore, we calculate the distance is n d lambda upon small d. Okay, now here n is equal to 1, 2, 3 and so on. So when we are using here n is equal to 1, so x1 is equal to lambda by d. When we are using n is equal to 2, so this will become 1 minute d lambda by d, and when we are using here n is equal to 2, so this will become 2 d lambda by d, and so on x equal to n, then we get the result is n d lambda by d. Okay, so this is the n bright of P. Clear? Now we will calculate the fringe width of the two bright fringes. Okay, so for calculating this, we just took here exceeding or preceding fringe n minus 1, either x, or we can use here n plus 1. N minus 1 I will do, x plus 1 you can use. Okay, so if we are using this, so this will become n minus 1 d lambda by d. Okay, and if we are using this, so this will become n plus 1 d lambda by d. Okay, from here just assume if x3 we are using here, so we will get d lambda by d. Clear? Now what is the difference between x2 and x1 and x3 and x1? So you will get x2 minus x1 is equal to d lambda by d only. Okay, so on solving this result, you will get xn plus 1 minus xn is equal to d lambda by d. This difference is called fringe width. Okay, xn minus 1, n plus 1 and xn minus 1 n is called fringe width. Okay, and denoted by beta or small w. Clear? Therefore, this will equal to beta is equal to d lambda upon me. This is the difference between the two bright fringes at P. Okay. Done. Next. For P is dark point or destructive interference. Okay. Yes, sir. It is clear? Okay. Now the path difference for destructive interference S2P minus S1P is equal to how much? 2n minus 1 lambda by 2. Clear? Where? So this we calculate from here. Fringe width for dark. Fringe width for dark fringe. Fringes. Okay. So the fringe width is depend on lambda, d, and small d. If you increase the source distance, then the fringe will decrease, and as near the fringe toward its center, so you will get the fringe width will increase. It means you will get the bigger fringes like this. Suppose the rays reached at point O dash by the two sources. So here we get a dark fringe like this because the two sources reached there. But after that we get first dark, second dark, third dark, fourth dark, fifth, sixth, seventh, and so on with the equal distances, and similarly below it. Okay, these kind of fringes are observed because the lambda of the source is same, so the pattern of the fringe reached to the spring is equally downward and equally here. So this distance is called beta for the constructive interference, and this distance called beta for destructive interference. These are the interference patterns observed in the case when the light source is traveling from two sources to a single point on the screen. Okay, we will discuss some more points in the next lecture. Okay, and then we will discuss about the diffraction pattern. Okay, here we need two sources, and in diffraction pattern we have only one source or more than one source. Okay, thank you.